now, we're recording.
I think the notation that you left off on, like reviewing that, would probably be a good place to start.
Sure. All right, so that would be the general game notation. So, and feel free to ask questions during this, and just don't raise your hand, because half the time we're looking towards the board writing, so just ask away, obviously. Okay, so for a general game, just as a slight review, if G is a game, that might be viable. Then we write as a set all of the left options, which I will denote X sub L and X sub R. So this is all options available to our left player. These are all the options available to our right player, and we just shove them in a set on both sides of this bar. Under some conventions, we need all these left elements to be less than all the right elements, but we're ignoring that convention for now because that doesn't get us all the interesting stuff that we can get from these games. That restricts us to only be the class of surreal numbers, which are nice. Like, it's a very nice class, but it's a little too restrictive. Like, we don't get stars showing up, and we don't get games such as -1 showing up, which are interesting. So we're going to ignore that restriction. So let's see. I wish I would have wrote down the addition and multiplication rules for these games because they behave sort of like surreals. I don't feel like doing that because it's very, very messy. Like, so messy I'd probably get lost trying to actually compute something. As unfortunate as that is. But yeah, once we have this notation, we can start messing around with things. So I guess, for instance, let's take a game where we define it recursively. I mean, we already kind of did that last time. We had a game that I labeled F, which was denoted by the options of left can go to 0 or right can go back to F. And we were working with that to see what its properties were. So for the Hackenbush position, is the recording working fine?
It's doing something.
Yeah.
Keep going.
We had, there we go. That's a lot darker. So for reference, the game F showed up as the game where we attached an infinite number of red stalks to a single blue branch. And we previously showed that this was less than any positive infinitesimal. So F is less than, say, epsilon to the omega. That's a bad omega. That looks like it's not even an omega, that's just a symbol. Where epsilon is 1 over omega. So I'll put that down. Now we're going to show that the game F minus n copies of down is positive. So that would be the game given by, well, I'll rewrite this somewhere else. Show F minus n copies of down is positive. That would be the game given by, right?
Could you refresh us on what down is?
Yes, I will do that immediately once I find a fourth color.
Sure.
We said orange didn't really work, did we?
No, it doesn't really work.
Okay.
Red stuff, yeah.
Yeah. Purple works, but it's almost indistinguishable from blue.
Well, so we use the most distinguishable color, and let's do dotted lines instead.
That works.
Yeah.
That works. Thank you, Kenneth. So that's sort of a dotted line. The game down was defined by, we had these 2 purple branches either player could chop, and then to one of them, we attach a solitary green branch that only green can chop. and now we just have n copies of this game. So I'm just going to put a little n under it. And we play the game f plus n copies of down. So that should be a plus sign, not a minus. Because we can't technically subtract games from each other, we can only add them. It's kind of, well, you're technically subtracting up, but you're adding down because they're additive inverses of each other. So let's think about this. We start from the game f minus n copies of down, or plus n copies of down. I'm going to keep tripping myself up on that. I'm sorry. So from that position, move that. Let's see, f plus n down. Well, red's best move, and by best I mean essentially the move they want to play to preserve the game. So green is never going to play in the down component of this game because they want to preserve as many downs as they can. If they reduce the number of downs, they move the game towards being more positive. And by moving it to being effectively more positive, they're making their loss faster. So if green were to play, they're going to only ever play in the f component. So they're just going to go back to the position f plus n copies of down. They're basically going to do nothing. They're going to pass, essentially. Blue, on the other hand, their essential best move is to cut the branch that's holding this red branch up. Because they want to deprive, green. They want to deprive green of as many moves as possible. So they really have two options. They can cut this branch, moving to the game f plus, I'll write it out. They move to the game f plus n minus 1 copies of down plus star. Or they could move to the game, this is sort of, I'll write it for completeness. F plus, they cut that branch, they're going to move to the game, which doesn't really have a value. It doesn't really, okay, it has a value, just not a good name. It's the game where you have a single purple branch, and then on top of it, you have a red branch. It doesn't really have a good symbol. I'm just going to denote it as that thing, for lack of a better idea. I mean, I can write it out in the set notation if you want.
You're not breaking the stereotype that mathematicians are bad at coming up with symbols and names.
I mean,
It was a G on top of a P.
Yeah,
Makes perfect sense.
That's true.
I can write it out like this if you want.
Sure, I'll accept it.
Honestly, yes, that's why I did it. Well, so this is blue's other move, to move to this position. Well, it's not exactly it. It's a good move, but it kind of leaves red a little too much wiggle room, or green. Again, okay, so the colors,
Blue and green, the ones that are on the board, but there's also these purple ones that anybody can cut.
Oh, the purple ones are the ones.
yes, so the players labeled blue and green can only cut their respective branch colors, but the purple branches can be cut by either player. So from these positions, we can sort of keep analyzing it. We take this to be a base game. We see what happens if red and green make their respective moves. Red would stay in this position, essentially. Green.
Yeah, I can tell in your notes you're used to doing this with red.
Yes, exactly. You can very easily tell.
Really tell.
Yes. Blue would essentially remove this star from the position. I mean, they could also remove an up, but it's slightly, I mean, either way, it's a good move. I think the quote-unquote best one is to reduce the multiples of up. Then you're left with f plus n minus 2 down plus star, which is star plus star is 0. But I don't want to say it's obvious, but it's slightly clear that as we continue this procedure, the number of downs is only ever going to decrease. Like, we'll eventually get to the position f plus k down plus some random junk. With k less than n. And this will kind of keep going. I don't keep wanting to use the argument of it has to stop at some point, but it does kind of have to stop at some point. Green can only delay the number of moves they have for so long. Eventually, blue is just going to chop down all of the downs because there's only a finite number of them. So we eventually reach a position where we're left with just f through any of these paths we take. I would explicitly show that, but I'm going to run out of room if I start trying to write arbitrary game trees on the board, unfortunately. So I hope it's clear. If it's not, let me know. No, seriously, please let me know. So this entire tree shows that f plus n copies of down is larger than 0, which directly implies that f is larger than negative n copies of down, but negative down was equal to up. So I will explicitly write that. So we have that f is larger than n copies of up, and simultaneously less than all positive infinitesimal values. Now that is, to be honest, when I first saw that, I was very much in the camp that that literally cannot be true. Because I'm claiming something that seems incredulous at the moment. I assume I am. But I have just proved it, so unless my proof is flawed, it should hold. I should mention, F is also known as the game we call over. Not for any real reason. The people who invented this stuff were, again, slightly bad at naming things, as most mathematicians are. Unfortunately. So this is the game over, and we've just shown it has this property. Yes, for any finite n. Once you get into infinite ones, I don't think it holds anymore. I'm 99% certain it does not. So I should specify n is contained in the natural numbers. But yes, this property holds for any finite n you want. A Google to the power of a Google, tree 3 to the power of tree 4 plus tree 7, stuff like that. Okay, so that's just kind of a fun property of over, and we're going to get into slightly more interesting waters. I say waters, but I should say positions. So with over, there is a corresponding negative game called under. Has the same properties. It's sandwiched between all of the negative infinitesimals and all the negative copies of up. So in the reverse orientation.
So the copies of down?
Yes.
And for the exact same argument?
Yes, exactly. The exact same argument will work. Basically, if you flip all the colors, the literal exact same argument holds, but just with the reverse inequalities. So under is larger than all of the downs, but smaller than all of the negative infinitesimals. I think I flipped that properly. So from here, we're going to go to, well, we have games with infinite number of, we have games with an infinite number of petals so far, but there's been one, I don't want to say issue with it, but if you notice, they're all connected to a single branch connected to the ground. So it's very clear that someone can win that game, obviously. Like, the only player that can win the game is the one with all the branches connected to the ground. There are ways around that. For instance, if we make the game... Oh, right, need to dot that. Sorry. There's a similar game to Over. Which is it's a purple stock with an infinite number of blue petals attached to it. Now it's not exactly clear who wins this game. Because whoever goes first is just going to cut the purple stock. It's almost like these infinite blue petals are doing nothing. Right? And you would be correct. They are sort of doing nothing. In the sense that in the game notation, this is also recursively defined. If we call this game D, then it has notation given by 0, D bar 0, which is slightly obvious given how we define the game notation. You notate down all of left's options, bar all of right's options. This game also has a name. This is where the names start getting a little bit more whimsical. This is called a pawn. I'm not joking about that. Or, wait, sorry, I think it's called a pawn star. Let me double check my note. Yes, it is a pawn star.
That's slightly more creative.
Which I am 99% certain about this, but the notation is a bit weird. This is the game a pawn plus the game star. Which means I need to make a slight correction to my previous talk. Whenever I wrote the notation star 2, it should really be star subscript 2. Because the book I'm basing this out of reserves the notation 2 star to mean 2 plus star. I have no idea why they do this, and I will not be following it. But they do this. They also do the same thing for mixed fractions. They'll write 1 1/2 to mean 1 plus 1/2, which, I mean, it does mean that, but it's also weird. I guess this book was written before normal fractions worked their way into math books.
Stop making excuses for them, just judge them openly.
Oh, very much so. I don't like it. I really don't like it, and it's annoying. Like when because I played this versus, I played a pawn star plus star and realized, well, I forget what I realized. It was a little bit, the notation gets a bit strange at times and very much not helpful. But yeah, with a pawn and a pawn star, well, actually, I haven't written out what a pawn is, so if you want, I can do that. Unfortunately, I don't know if there's a Hackenbush position for it. But the game a pawn itself is also recursively defined to be the game where left can move to a pawn and right can move to star. And that's how they win, basically. Like I said, I don't think there's a Hackenbush position for that. It just happens to sort of exist.
So there can be games that don't have a Hackenbush position, I thought.
Yes. At least to my knowledge, there is no Hackenbush position with this game notation.
So, like, you generalize the idea of game to sets of moves as opposed to, like, actual
Games.
physical drawings of things. And does that leave you with a connected line, or do you need to do some sort of completion process to get the full
Well, if we allow things like this, we're larger than the surreals already.
Okay.
Because remember, star is not contained in the surreal numbers.
Okay. These things plus some extra conditions allows you to produce the connected surreal.
Exactly. This is essentially the, I don't want to call it the disconnected surreal line because it's not even really the surreals, it's larger than them. But I guess you could call it that. I mean, I don't think it makes any sense, but
Well, I mean, I don't necessarily, if this thing is larger than the surreals, isn't it? I suppose I don't necessarily know
Does this
what.
larger field have a name?
it's just the class of all games. It's not really a field. I mean,
Does it have an,
I mean, I think it's a
surreals
field.
have an ordering, but
I mean, you could
these
argue,
don't really have a consistent total.
not that I'm aware of, no. I mean, you can probably get a partial order on them, but I don't think total.
We clearly have the partial ordering that we've been learning about.
Yes, I haven't explicitly written it down because neither do these guys, unfortunately. At least not in as many words. There are ways to get it out of the things they're doing, but I haven't actually explicitly constructed the partial order myself.
So Logan, so if a pawn is defined recursively, right?
Yes.
So then how do you get that? Did you get that a pawn plus star equals D because you used the just the notion of addition like how it's defined to show that this relation does exist? Because you can't write down like you can't write down the Hackenbush position for the pawn. Right?
As far as I'm aware, you cannot. Actually, I might, okay. If I go back to the section on infinite games, just give me 1 second and I might be able to write it down, but it might look very silly. Then again, half the things I'm writing down look very silly. So give me 1 second, please. Where is the diagram of all those positions?
So the real line and then also the surreal line, they're connected topological spaces.
It's done.
Meaning essentially the equation is complete. So what that means is if you came up with a sequence of games, it would be more interesting if every single one of them corresponded to an actual position in the sure that you could draw. But every single one of these games, if there was a metric that you could put on them coming from this ordering that we get, and you could establish a sequence of functions Cauchy, then it would necessarily approach something.
Is there a metric?
It would, well, you
It's
could,
only partial order, right?
yeah, just a partial order.
I mean,
It's just connected as a topological space. That's all.
I mean, you can do integration over the surreals, sort of.
It doesn't require connectedness.
No, it doesn't. But Paneth, going back to your question, game addition is similarly defined to, I want to say it's similar to how we define addition for the surreals, which I'd have to look up again. It's in my notes somewhere. But I do believe you would basically take this, add to it the set defined by star. Well, no, because the set defined by star contains all zeros. I don't know how you would actually get this thing. I'm not even too sure this is actually correct now that I think about it. This is the trouble with their notation. I don't know if they mean the game a pawn plus star or just a pawn star is its own thing.
So from what you're saying, if star is just a bunch of zeros, then it seems like addition won't actually help you in this case. So maybe
Right.
that pawn star is probably just its own thing.
That's what I'm assuming, because that's what I'm basically going to have to assume for now until I can be shown otherwise, unfortunately.
Okay, it's fine. As long as it doesn't affect the rest of the
No, I mean, star will show up again because it kind of always lurks in the corners. Right, so we have some weird things like a pawn star. A pawn star is unfortunately the last weirdly infinite game we have a Hackenbush position for. I mean, it's not the last recursively defined game we have a Hackenbush position for. It's just the last funnily named one we have a Hackenbush position for. But I went into this tangent on recursively defined games because the next thing I'm going to write down is also a recursively defined game. And if I write over here, can the camera still see me?
Yeah, we're following you.
Oh, that's comforting.
Technology.
We have technology.
That's comforting. So I'm going to write down a game which is, so all of these blue stalks are going to be connected to the ground, which I am going to write. And there's just an infinite number of them going off to the right, forever. So, just as a quick question, what do you think the value of this game is? There are no wrong answers.
It looks like negative, is it negative infinity or positive?
Well, we declared blue to be a positive, so these would be a bunch of positive ones being added together infinitely, essentially.
So omega? Not omega.
You're close. Your second statement was close, actually. It is not omega, as in its not value is not that of how we defined omega, because let us play this against the game minus omega, which is an infinite number of green stalks going up. So let's see. Blue makes a move, cuts down one of these blue stalks. There's still an infinite number left. So green makes a move. In this infinite number of stalks, they have to...
Pick a finite number to start.
Exactly. They pick a very large finite number, and they declare that's how many moves they want to make. So,
No matter how big it is, it's still smaller than infinity.
yes, exactly. Because the way we define omega was an infinite number of stalks going up. They have to select a position where once they cut it, they're left with a very large but finite number of moves left to play. So let's say they just decide to cut it to where they have, I don't know, a googolplex number of cuts left. Then for the next googolplex number of turns, they're just cutting down from the top of the tree until they run out of moves. And blue is never going to run out of moves. So we have that this position, whatever it is larger than omega. Because it's omega minus x minus omega is bigger than 0. Similarly, if I, on top of this infinite stack, if I add another green branch, that brings us to negative omega plus 1. By the exact same logic, the previous argument holds. And for omega plus 2, omega plus 3, omega times 2 is 2 copies of omega stacked on top of each other. If you cut down anything in the first infinite section, the entire top of the second infinite section falls with it. So this thing's also larger than omega's times 2, which I'm going to write as omega 2, and omega squared, and omega to the omega, because every single one of these omega patterns is an infinite stalk going up. And it's larger than epsilon naught, the limit ordinal of the omegas, and epsilon 1, epsilon 2, epsilon n. Basically what I'm claiming is this position x is larger than any possible positive surreal number.
Is there a way, besides going through various examples with big numbers, to show that it's the biggest group?
Unfortunately, no. You basically have to explicitly, okay, there,
How much you just said there is total order in the big field?
well,
By the notion of the biggest that there's no.
Well, I mean, you
Because
have to say
we-
everything comparable to him is less than him.
because
We haven't
we,
necessarily shown this.
and we are also now outside of the surreals. Once we introduce this element, we're outside of the surreal numbers and back into the class of games. because the notation for this game violates the first axiom of the surreals in terms of their notational definition. Because X is the game defined by X bar nothing, which, keeping in mind that if X is positive, as it is, we violate the first rule of the surreal numbers, where all the left options must be less than the right options. There are no right options, and this thing is positive. So it's not less than the empty set. So this is not a surreal number. By definition, it cannot be. So we've stepped outside the surreals, which is why I can claim this thing is larger than any of them. I technically haven't shown it to be larger than any of them because there is no largest surreal number, as expected.
You could find a sequence of increasing
Surreal.
numbers and then show it was larger than every single one. If it was a
Yes.
sequence that was eventually larger than any other surreal.
Yes, and you can do that with the omega to the omega sequence. Well, after you get to epsilon naught, you kind of have to, after you get to the first limit ordinal of the Peano axioms, you kind of do some weird stuff to get past that. But once you do that, you're essentially home free until you get to the Bachman-Howard ordinal. So this thing, likewise, has a negative game, which is just an infinite number of green stalks, which is similarly to this thing less than any negative. Is it less than?
Less than any surreal.
Yes, it's less than any surreal, yes. And we call X and its negative, well, X is also called on for ordinal number thing, or because it's larger than the set of all ordinals, essentially. And its negative is, well, take a guess, I'll give you one. Exactly. Its negative is off, which has the exact opposite notation. Off is the game, nothing bar off. Now, the real question, what happens if we add them together?
It's negative.
Probably, but let's find out.
Then again, analysis would tell us that infinity minus infinity would be
Infinite number of stalks, infinite number of stalks, okay. Well, we did show that omega minus omega last time was the zero game, in essence, because you just use the mirror strategy against your opponent. But in this case, there really is no mirror strategy because, well, anytime we chop a single branch, there's always an infinite number left for both players. It does not.
there are no choices of moves you can make.
Exactly. Which is why it is technically not a combinatorial game. Because there's one condition I have not stated about combinatorial games, in that we like for them to end. We like for combinatorial games to actually have an ending to them. This is a drawn game. And we write it, so on plus off is also known as dud, for where dud stands for deathless universal draw. Notationally speaking, it's the game dud bar dud. Because it turns out this is isomorphic to a game where you have nothing but infinite green branches, or purple. Because when you chop something, nothing changes. Which is why it is not the same thing as the game where I shove on and off into both sides of this, which is not representable in Hackenbush. I only want to try to think about what that would look like. But yeah, this is the game dud, and it's recursively defined as for most of this weird stuff. It's not combinatorial because it is a drawn game, but it is weirdly interesting, and it does show up a bit, slightly. Yes. Yes. Correct. Correct. Yes. So it will by itself never end, but once the second player gets their turn and they have no moves, they lose. Yes. Once you have no legal moves left, you lose the game. All right, so we have on, we have dud. Okay, I guess we're going to go to the speed round. I say that because this is going to be the, I don't want to say collection of weird stuff that didn't fit anywhere else, but it's kind of the collection of weird stuff that didn't fit anywhere else. In essence, I am now going to write two things on the board, and then I think that will sort of, I don't want to say end of the talk, but there we go. I kind of need that to reference that. Okay, so the last thing I want to talk about are things called tiny games, which, while we're in the land of recursive games, you might as well discuss those. So the game tiny sub g is defined by 0 bar, 0 bar, negative g. It's this thing. And these things are very, 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 very small. Well, except for tiny up. They're all positive, I should state. Oh, Bryce, for the 5 seconds you were gone, I'm starting to introduce the tiny games, which are also recursively defined. They're all very, as their name implies, they're all very small. They're all positive due to how they're defined. Okay, it's not exactly clear they're positive, but they are. Due to the fact that, yeah, since left can win by immediately going to the 0 game, they're all positive. Okay, so this thing G can essentially be any other positive value we want. We could shove 1 into there. We could shove star into there. In fact, I can't actually prove this, but it happens that up is the unique solution to, well, not that equation, that's just wrong. I'm not, never mind, please ignore the past 5 seconds. Yes, so tiny games do show up, just not in Hackenbush. Like in the game of domineering, they'll show up as natural values of games. But the thing I want to introduce is what happens if we just shove on into this set? Like, we can do that. It's a perfectly valid tiny game, the game tiny on. Well, given that these games are so tiny, it turns out this game is larger than 0 because on is positive. This is smaller than, well, let's see. On is larger than any possible positive surreal number. So tiny on is sort of the inverse. It's smaller than any other tiny game where if we have 2 games, G and G prime, if G is less than G prime, then tiny G prime is, yeah, flip this. So that holds. What I'm basically claiming is tiny on is less than any other possible tiny game. So like say tiny omega, or tiny omega plus 1, whatever you want really. And is therefore the smallest possible value of a game we can ever possibly have. because on plus 1 is equal to on. So on is essentially a fixed point of addition and multiplication. But, so all of these tiny games, they are all less than up because they're all very, very small. And let's see, I wrote down what I call the grand cavalcade of the Nimber line. I went sort of whimsical on the naming. So we essentially have all these tiny games are less than up, and they're all infinitesimal. Keeping in mind that up itself is all infinitesimal. Then up is less than over, which is less, well, over comes after all the ups. Right, I wrote this down and I'm still losing my notes. So this is less than any finite combination of up arrows, which after you do all those is less than the game over, which is less than any possible positive surreal number, which are all less than the natural numbers, which are all less than omega, which is less than omega plus 1, which is less than omega squared, which is less than omega to the omega, which, once you get past an infinite sequence of that, is less than the limit ordinal epsilon naught, which I've never discussed, but it's large. Then you keep going. Epsilon sub epsilon naught, epsilon sub epsilon sub epsilon naught. You keep constructing more limit ordinals that get weird, and it's outside the scope of this talk, unfortunately. Then you get to the game on, and the exact same thing works in the reverse direction if you flip all these inequalities and signs. You go from the game called tiny to the game called miney. Let me notate that. This thing is typically called tiny. I can't bold it, but it's typically bolded. I can't really bold things on a whiteboard, unfortunately. Right. I just wanted to introduce that because it's a very weird concept to think of. This thing is the smallest possible positive value once we introduce the game on. Like, there's nothing smaller than this except 0. Like, literally. And then there is a single thing I would like to write out that is just a funny little object. Once I find the markers. Mostly because I found it funny in the book, and it is just kind of a gag. Okay, so at the end of one of the chapters, I don't know why I'm erasing this left-handed. They have a drawing of a Hackenbush position, or if I remember my colorization properly, yes. 1, 2, 3, 4, yes, 9. I need 9 separate. Okay, there's the ground. We have 9 separate branches coming up. All connected to, let's see, 1, 2, 2, 2. Okay, that's purple. These next two are blue. Where'd I put the blue marker? Likewise, these two are blue, the rest are purple. I do not know how these gentlemen found this position. I am surprised, somewhat. Let's see, those two coming off the edge, those two coming there. Connecting here, connecting here. This is going to be annoying. My artistic skills are not exactly good, so I do apologize.
This one looks like a 7-Up bottle.
Yes.
Wait for it.
You gave away the joke. Thank you.
Thanks. We did this last time. How did you?
No, we didn't. I never actually explicitly. wrote it down. I was saving it for the end. But yes, I'm trying to draw what looks like a 7
Show
up.
me the picture, and I was just sitting here like, don't spoil it, don't spoil it, don't spoil it. And you saved me the embarrassment.
I thought everyone was here, the last time we were here, right? We were talking about it. What does the 7 up look like? You said it looks like a bottle.
No. Just you, I guess.
Who's there?
Um,
Now I remember.
Thank you, Phil. Now you remember.
Yeah, but I didn't remember before you said it, so.
Why are there so many different colors? There's only 3 of them, and it's still, there's so many separate branching points. I hope this is coming across properly. I should have just turned the projector on. It might have been quicker. And I think we now need, you know, thank you for the idea. What was that?
People with additional advice.
Yeah, thank you for the idea. I will keep that in reserve for the, if this ever occurs in the future. But I don't think there will be a part 3. I don't have enough material to pull a part 3 off.
We can do a better edition of this for an hour.
We could. I'll have to practice. But this position, it looks like a bottle. I hope it looks like a bottle.
Yeah, just believe me, it looks like a ball. The only thing that's fighting against its bottle identification is the fact that it's got a little bit of a gradual slope to it that most bottles don't have.
Yeah.
It wouldn't be a very good fit in the hand, it's not very ergonomic.
It's handmade, it's a craft work.
No, but it turns out this position, anyone want to take a guess as to what the value is? I wish Sprite was a...
Yeah, I'm at a loss. What's the value here?
Okay. Why do I find that so funny?
What is that?
It should be,
What should be?
should it be 7 up?
Exactly. This bottle has a value of 7 up. No, I am not joking. It actually has a value of 7 up.
We talked about this last time.
I was
I don't know. I don't know what you're talking about.
I was there. Thank you.
Like, in the extras, they just say it has a value of 7 up, and yes, they made the joke intentionally.
Not quite. That's right there. My spider senses were just slightly shifted.
Yeah, the exact quote is 7 up, together perhaps with some additives of no atomic weight. This is effectively where I wanted to end the talk, as I've sort of run out of normal things to talk about.
Thank you.
You're welcome.
Questions, comments, concerns?
Sure.
Is there any rate structure you can put on the class of games?
I mean, I think they form an abelian group. I'd have to reread a paper or two I found on it. But I believe they form an abelian group.
The operate from the earlier.
Yes, the operation of addition on games is not easily defined, but it sort of works like the surreal numbers, but you have to extend it a bit, I think.
I think Bryce has a question.
Yeah, just spit it out.
So we know about these surreal numbers and that's complete forms a connected set.
Yes.
But when it comes to all games, we saw that we only ended up with a partial order set,
Yes.
or at least from what we've seen so far. Do you know if the largest totally ordered subset of that guy is also connected?
The largest totally ordered subset of games should be these surreals. Because I can't think of anything else that would be totally ordered and connected that is also not isomorphic to the surreal itself. Well, that is also the largest class of its kind, I should specify.
So the notion of giving value to the game,
Yes.
it seems like it's sort of like some vicious cycle of being an artifact of naming, but then the naming itself comes from finding actual correlation between numerical values and the way you name.
Yes.
So is it true that you can't really give one thing most of the credit. It can't just be an artifact because there's a lot of these numerical connections that actually exist. But you can't just be the numerical connections because we're also sometimes arbitrarily naming, right?
Yes, like the game Upon and Over and stuff like that, those names are essentially pulled out of a hat. Like, you don't need the names themselves. You could just use these positions to represent games and you'd be fine.
Exactly. So then my question is, was part of this talk, because I want to have a follow-up. So part of this talk was to, because it's a really fun thing to actually think about, that they have these things. They have all these properties that are also satisfied by numbers.
Yes, and we have
The
these games.
progression of this talk, one of its points was to showcase all the different whimsical things that come out of it, all these connections. Was that part of the point?
Yes.
Okay, in that case,
Yes.
did you have in your process of creating this stuff, did you have anything that you threw away because you thought there wouldn't be enough time, or maybe you thought it doesn't have a good progression with the rest of it, but there's something that you totally challenged?
Yes, there's a whole actual theory behind games with recursive positions, denoted in terms of things called stoppers and enders and things like that. Like, there's actual mathematics behind this that I didn't feel like discussing because it would have not buried everything under it, but it would have been a bit much. Like, even I am struggling to wrap my head around some of it. Yes, exactly. It's very technical.
It doesn't showcase the magic of the subject.
Yes, I mean, it's there. It's good theory and everything, but it's not something you want to show off in the first bits because it's technical and a bit very abstract, slightly awkward to deal with, and just in general doesn't show off. Not as whimsical as this can be, but as interesting as this can be if you're just staring at these game positions with no actual position to look at.
Yeah, you wouldn't want to drown in the details. So it did.
Exactly.
So, any more questions? Okay, looks like a good speaker again.